Hello everyone. Thank you all for attending today's presentation on Introduction to Physical Design. This presentation will give overview of synthesis and place and route. Before going to our presentation, let me introduce myself. My name is Sanyasi Apparao 𝗧𝗧, currently working at Moschip Technologies as Director of Engineering Physical Design domain. Graduated in Electronics and Communication Engineering, later trained in Physical Design. Overall 19 years of experience in synthesis and physical design domain. I started my career in 2006 at TTM Private Limited, India. Later, I worked at 𝗧𝗧 Semiconductors as a lead engineer and manager. Then worked as a senior manager at Moschip Technologies and now become Director of Engineering in Physical Design domain. In my career, I worked on various technology nodes all the way from 180 nanometer to 4 nanometer. Handled critical designs with high frequencies and multi-million instances. Involved in multiple tape-outs with tight schedules. Also worked on the designs with low power implementation. Overall, I have good knowledge and strong hands-on experience in synthesis, place and route, static timing analysis, DRC LVS, EMIR analysis and logic equivalence areas. Thank you. Let's move to today's presentation, Introduction to Physical Design. Before going to our presentation, let me talk about ASIC. Because if you know about ASIC and its methodology, then we can understand where exactly the physical design flow plays a role. Agenda of today's presentation. Overview of ASIC and introduction to ASIC design flow. Physical design flow, which includes synthesis and PNR. That is our main topic today. That is RTL to GDS2. Sign-off checks before tape-out and career opportunities in physical design domain. Overview of ASIC. For a desired application, we should start with specific design targeted to particular application, and we need to work on the implementation to reach that particular application. It is a application derived, means application specific integrated circuit. The typical components in ASIC: I/O pads, core logic, memory, IPs, metal layers. If you take any typical IC, you can see these components. I/O pads. These are inputs and outputs of the chip. A chip has these inputs. These inputs and outputs will connected to the external world and to our internal logic, core logic. Core logic is main functionality of your design and chip. Mainly the digital gates. In your academics, right, you studied about AND gate, OR gate, all those is a part of this functionality of the design is built with digital gates. That is called core logic. Memories. Every chip required some memory. Those memories generally with SRAMs. Those are all called hard macros. And IPs. Depends upon your design requirements. You can have different IPs. I am taking one example, PLL, phase locked loop, which is helping you to generate the clock for your system. Similarly, you have other IPs like USB, DDR. Depends upon your application, we can choose the required IPs for your chip or ASIC. Metal layers. Every chip consists of power and signal nets. Means every digital gate, if you see, right, VDD, VSS power and inputs and output signals and clock signal. All these power and signal nets connected through these metal layers. Physical view of a chip in PNR tool. Just I want to give some picture how a chip looks like. If you look at periphery, top, bottom, left, right, all surroundings you have the green color, those are called I/O pads. And top right, if you see bigger ones, those are all memories, nothing but SRAMs. Bottom left, if you see PLL, it is IP, we placed it at bottom left. And at the center, core logic, digital gate, those are all digital gates. And metal layers, which are useful to connect power and ground connections and signals in your chip. Different levels of your design. If you take any chip, any design, you have different hierarchies. First is system level. It is a top view, you can say, system design level. Then it is made up of with different modules. Next one is the module. Different modules and IPs come together and it forms a complete design system. And these modules will be a combination of standard cell gates. If you look at, right, 4 input, it is an AND gate. So similar kind of gates come together and create a module. And that is called gate level. Next is circuit level. These gates build up with transistor level circuits. So in next level is circuit level. And these are CMOS gates, means PMOS, NMOS you have in circuit level. Next level is the device level. All these PMOS and NMOS gates built with polysilicon, N plus, P substrate, like different layers. That is the device level. ASIC design methodology. Generally, this ASIC design methodology starts with specification, then next level is coding and verification, then physical implementation and fabrication and packaging. Of course, we can see more details in the coming slides. ASIC design methodology generally consists of front-end design, that is one part, and logic synthesis, DFT and STA, and physical design. Front-end design. Your front-end design starts with system specification, then architecture or design level, then RTL coding, design verification or RTL verification. These are the different steps in front-end design. Then finally, the output is Verilog files, RTL files to the synthesis. In the front end, first step is the system specification. Generally, it is called spec. Depends upon your product application, performance, the kind of memory required, and features you are targeting, interfaces of this product. Depends upon all those parameters, you need to decide the spec. For example, I am taking a product, can be a laptop, smartphone, smart TV, anything. So, depends upon the features required for your product and performance you are targeting, you should come up with a specification. Once the specification is decides, you need to go for the next level, nothing but design or architecture level. So, once spec is decided, the specification we should pass to design team. Design team start working on different components or IPs required to meet these specifications or target performances. Once the design is completed, the design details will go to the RTL design team. RTL design team, first one is the RTL coding. RTL means register transfer logic. Using any hardware description language like Verilog and VHDL, these are the two languages which are the hardware description languages. You should convert entire design into the coding. And a hardware description language is a software programming used to model intended hardware. It is a technology independent, means this RTL we can target to any technology node. Of course, we can see more details on the technology related. I am showing a sample code of simple design, how it is look like. RTL code. Our module name is in this latch single multi. It is a module name. Then what are the inputs and outputs? What are the different components in this RTL code? It's a simple code, small code. Once RTL design completes, coding is complete, then we need to do the RTL verification. The design verification team using a test bench, means input patterns, they will do the RTL verification to ensure the functionality of your design. While converting this design into the RTL code, we should not lose any functionality. I am showing a simple snippet of how the waveforms looks like on a design verification stage. So, once the RTL verification completes, you have the RTL code. That is input to the next stage, nothing but logic synthesis stage. I am taking simple example for a chip design. I am taking smartphone, that is our product. We are intended to go for a smartphone. A smartphone consists of network like Wi-Fi, 4G, Bluetooth, and CPU, mobile applications, frame rate, and displays, video recording, camera, like that. And also how much memory we need for this product. So these are all comes under specification. once the customer come with the required specifications of a targeted application or product, okay, how much quality and what is the performance, then those details we need to send it to the design team. That is called architecture team. So design team looks at all required IPs or components and they come up with required design to meet those, let's say, video quality, targeted frequency, all parameters, application features we should meet with a design completion. Yeah, before going to our next stage, we are completed with the front-end design. Before going to the next stage, let me talk about the role of analog team, analog design and analog layout. See, if you recollect slide number 4, we discussed about the different components of an IC, I/O pads, IPs, SRAMs, standard cells. All these are predefined cells available in the market for a particular technology node. All these IPs and standard cells will be prepared by our analog team for particular technology. See, if you take a fabrication house, example, TSMC is one of the famous fabrication house. So, if you target for a given target technology node, we should prepare all these IP standard cells and I/O pads and memories with help of the analog design team and layout team. Means the analog design team and layout team initially worked on these required components for a technology node. Those will be used by our digital team at architecture or implementation levels, available IPs. And one more topic, technology information. First, what are the different layers in a CMOS? N-well, P-substrate, polysilicon, N+, all these are different layers. Of course, metal layers for the interconnections. All these are different layers in a device level. To design a product, we should choose the right technology node. What technology node we are going to target to implement this product? For example, smartphone. What is the technology node? Like TSMC 28 nanometer or TSMC 40 nanometer. First, we need to choose what is the technology node. TSMC is the fab name, and 28 nanometer, 40 nanometer, that is indicates the node. Node, that is the channel length of any CMOS gates. In your CMOS circuits, right, you have channel length. That channel length indicates the technology node. It is constant for a given technology node. Design rules. All CMOS devices are fabricated and connected through these layers, whatever the layers we discussed. We should follow design rules given by the fabrication house. Like TSMC is one fab house, Global Foundry, GF, Samsung, Intel, these are the different fabrication houses. They will provide a set of design rules, minimum width, minimum spacing, enclosure rules, like that. We should follow all these design rules during the fabrication. For a given technology node, we have set of design rules. Those will be varied one technology node to the another technology node. All these design rules will be captured in a file called tech file or tech-lef. Generally, this analog team will dealt with base layers. These layers are categorized into two. One is base layers, one is metal layers. Analog team deal with base layers because they are working on preparing the standard cells and IPs, right? So, they dealt with poly layer, N-well layer, all these called the layers present in a device called base layers and metal layers, second category, which are helping for the interconnections and power connections on the chip. The digital team generally deal with the metal layers. Analog team deal with base layers and also metal layers. Including these base layers and metal layers, will create a file called, all design rules, tech file used by the analog team. And for the digital team, the base layers information is in general not required. So, we will capture only metal related design rules in a file called tech-lef. That is one file which is useful in coming stages. Next one is the predefined cells, like standard cells. Analog team prepared these standard cells and SRAMs, PLL and I/O pads, right, for a given width and height. They target all these cells for a given area by choosing different widths and height values. And also, if you recollect your CMOS has the VDD, VSS pins and input outputs. For example, take a simple inverter. Inverter has the VDD pin, VSS pin and input A and output Y. All these pin information and height and width, these are called physical information. All this physical information of all predefined cells like standard cells, IPs, memories, IO pads, captured in a file called physical libraries. Those are called LEF files. This is also one of the input in the coming stages. Then timing libraries. See, if you recollect your academics, every gate has delays, like propagation delays. Means by giving the input, at what time you will see the response at the output. So that is called cell delay. Similar to cell delay, you have the power consumption values and area of that cell and what is the output transition times 0 to 1 and 1 to 0. All these called cell parameters. All these are characterized for a given cell and put them in a file called library, because those details are required during our logic synthesis and place and route. So we should require all these parameters during our logic synthesis and place and route. These can be different values. Those can be varied, depends upon your implementation stage. For that, what the fabrication people or library vendors can do, they will characterize those values for a given input transition. Means with what rate the signal is coming and how much load it's going to be drive at the design implementation stage. So the cell delay depends. There is a multiple combinations can be happened, depends upon your design. So for that one, what they will do, instead of mimic all those combinations, I can say infinite combinations, right? So to avoid that one, they will put a range, minimum and maximum, minimum input transition and maximum input transition, minimum load, maximum load, like that. For a given range of transition and load values, they will characterize the cell delays, power numbers and transition, output transition times and area also. All these captured in a file. Those are called timing libraries. Generally, people will call libs, dot libs. These are also inputs for the next stages. Now coming to our logic synthesis. If you recollect ASIC design methodology, first part we completed front-end design. The output is RTL code, Verilog or VHDL. Now the next stage is the logic synthesis. Logic synthesis is a process of converting our RTL into logic gates, digital gates, conversion of this code. The inputs for RTL, the inputs for logic synthesis is design RTL, Verilog or VHDL and constraint. The next input is the constraints. What are these constraints? Every ASIC, every chip is targeted for a performance, means everyone wants to run at certain frequency. And also other two parameters are power and area. Yeah, frequency is nothing but performance. First P is performance, next one is the power consumption and the next one is the area. Every chip designer always targeted for the maximum possible frequency, best performance, least possible power consumption and least possible area. These are all PPA targets will be consolidated and put in a file called constraint file. At what rate, what frequency, what power value and what area. And that is the second input. And next one is the timing libraries. Already we discussed. Thus every gate has the parameters, cell delay, power values, area and transition times. All captured in a timing libraries. Already we discussed about that one. But one more word called targeted PVT condition. What is this PVT condition? P means process, V voltage, T temperature. Every cell parameter changes by changing this process parameters and voltage and temperature. This PVT condition. I will explain. process variation. If you recollect your fundamentals, it is every CMOS is a device level. Means oxide thickness, N-well doping, and P substrate, and oxide P plus, P substrate, N-well, all these are all device levels. You have the doping levels and oxide thickness, right? Yeah, PVT, process. Oxide thickness, doping levels, all, taking two parameters of the process variations. This comes under process parameters. To design a gate, I think now we are getting the call. Let me answer that call before going to our topic. Hello?
హలో సార్, నా పేరు మానస సార్. నేను హైదరాబాద్ నుంచి కాల్ చేస్తున్నా.
చెప్పమ్మా మానస.
నాకు ఒక చిన్న డౌట్ ఉంది సార్. ఇప్పుడు వాట్ టైప్ ఆఫ్ లేఅవుట్ టెక్నిక్స్ హెల్ప్ మేనేజ్ హిట్ డిసిపేషన్ ఇన్ హై పర్ఫార్మెన్స్ చిప్స్ సార్?
Yeah, layout techniques for high performance, huh?
High performance chips లో layout techniques.
Yeah, I think that comes under analog layout design. I think discussed in the last session. You have the different techniques to achieve the best possible design. ఇప్పుడు ఇందాక మనం చదువుకున్నట్టు IPs, standard cells, all should be following some kind of guidelines to get the better delays, least power, like that. I think that is part of analog design. Digital designs lo kuda we have different techniques to meet your performance and power numbers. So if you look at the slide, right, optimization is one of the step to achieve the best techniques anamata. But layout techniques anedi analog design layout team sambandhinchindi. I think మీరు లాస్ట్ సెషన్ మీరు చూసేటట్టయితే I think you will get those layout techniques. Okay? Digital design related optimization techniques you can see in the coming slides. Thank you. Process parameters. To get a digital gate, for example, I am taking inverter. If you want to fabricate an inverter, you need N plus dopings and oxide thickness. Then say typical, I am using one word called typical, means if you want to design a simple inverter with a particular parameters, for that one, you should come up with a certain oxide thickness, certain doping levels. But during the fabrication, you may not get the exact oxide thickness and doping levels of N plus or substrate N-well. There is a deviation from your typical value, expected value. Okay? Because of those deviations, means if the N plus carriers varies from the expected value, oxide thickness varies from the expected value, then this will impact your cell delay and power consumption. Those variations also we should accommodate, but those limits should be within a acceptable range. That is process variations. And next one is voltage. Even every chip designer wants to run a chip at a particular voltage. Let's assume that is a typical voltage. For understanding purpose, I am taking 1 volt is my typical voltage. Let's say your chip is operating at 1 volt. If you recollect I/O pads have the signal pads and power pads. For the power pads, we are applying the 1 volt. Is that 1 volt is going to the transistors or not? We need to check. Because this power pad is connected to transistor power through metal layers. Those metal layers has some resistance value. Because of this resistance, you may see some drop. Because every transistor draws the current, IDS. That current is flowing through these metals from the power pad through the metals to the transistor. Finally reaches the VDD pin of the transistor. So, because of the current flow and resistance of these metals, you may see IR drop. Because of the drop, even though you are applying 1 volt, that 1 volt may not be reaches the transistor. It less than the expected voltage. The voltage changes, decreases from the expected value. If you recollect your fundamentals in academics, IDS of the CMOS gate depends upon the applied voltage, VDD. If the VDD is more, IDS is more. If the VDD is less, IDS is less. If the VDD the value supply voltage is reduces, IDS current will be reduces. If the current reduces, it takes more time to charge the load. The gate drives some load, right? It takes more time to charge. Means it takes more, you will see more time to see the response at the output. Means your propagation delay, mean the output response delayed, your propagation delay increases. On summary, the change in voltage is impact change in delay. Voltage variations is showing impact on the cell delay. Similarly, your power dissipations, static power or dynamic power, you have the power dissipations, right, in the CMOS gates. Those power dissipations also will be impacted by the applied voltage. Mean the cell parameters are changing with voltage variations also. Next one is temperature. It is junction temperature of the transistor. Generally, the typical value, junction temperature value is 25 degrees. Because of the on-chip power consumption or surroundings, the junction temperatures may be vary from 25 degrees. If the temperature varies, the threshold value of the device will be impacted. Means the minimum voltage required to form a channel in CMOS circuit. If the threshold value changes, it will impact your cell delay and power consumption also. Means the change in temperature also will impact the cell parameters. Process variations, voltage variations, temperature variations, all these three parameter variations will be impacted your cell parameters like cell delay, power consumption, transition values. So, I am saying targeted PVT condition. What do you mean by this targeted PVT condition? As I said, we are expecting some certain process parameters, voltage value, temperature value. That is called in general typical corner. And we have an acceptable range, that range given by the fabrication house for this process, voltage and temperature deviations. One extreme corner is called slow corner, one is called fast corner. Slow corner means because of these process variations, the cell delay increases, maybe decreases. Because of the voltage variations, the cell delay increases, may decreases. And the temperature variations, the cell delay may increase or decreases. The increase in cell delay because of this PVT conditions, it is because of this PVT variations. That is one condition, slow corner. Because of process variations, because of voltage variations, because of the temperature variations, you will see the more delays for any gate. Whatever the gates you have in your design, all the gates will experience the more delay. That is one called slow corner. Slow means more delays. Slow means speed, your speed becomes slow because of the more delays. And next one is the fast corner. Because of the PVT variations, the cell delay may decreases also. Means fast, your system becomes fast. That is called fast corner. Now we have three corners, slow corner, fast corner and typical corner. Which corner libraries I need to choose while running the synthesis? That is called targeted PVT conditions. Yeah, if you look at the right side diagram, you have the Verilog and VHDL. That is the RTL code. First step is translation. Means we are converting this RTL into the gates, logic gates. If you see inverter, AND gate, OR gates, all RTL is converted into gates, translating into the logic gates. In fact, that initial stage after translation, it is a generic one. You don't have any parameters, specific parameters for those gates. Means you can't see any cell delay, power numbers, area numbers for those gates. That is called generic gates. The next one is the mapping. Mapping means, as I said, you need to choose the target technology node. For the technology node, you are expecting three corner libraries, slow corner, fast corner, typical corner. One of the library we need to choose. By choosing that library, whatever the generic gates you have, we should map those generic gates to particular technology, so that after mapping, you can see the cell delays, area numbers, power numbers, transition value for all your gates present in your design. That is mapping to particular technology node. Okay. So, after mapping, one next step is the optimization. Let me explain what I mean by this optimization. As I said, after mapping, you are seeing the cell delays. Let's take this schematic. There are four inputs, A, B, C, D inputs you have, and output Y. A to Y is one arc, one path. B to Y, C to Y, like that you have the multiple paths from the inputs to the output. What is this performance check? Performance check means how fast the signal is coming from the input to the output. For example, take B to Y. I am applying a signal at a B input. The change in signal at a input B, after what time you are seeing the response at the output. That is, we can say performance check, means how fast it can come. After mapping all the gates, let's say one of the possible combination for B to Y is AND gate followed by OR gate, AND gate and OR gate. 4 gates are present in that path. Okay? As we discussed, slow corner has more delays, typical corner certain delays, and fast corner has the less delays. Let's discuss about this path B to Y. Let's assume that for understanding purpose, each gate taking a uniform delays, I mean common delay for each gate. 2 nanoseconds, inverter and gates, every gate is taking the 2 nanosecond in slow corner for a given input transition and output load. Okay? And a typical corner. In a typical corner, let's assume that each cell delay is 1.5 nanoseconds. And coming to the fast corners where you are seeing the less delays, let's assume that 1 nanosecond for each gate. 2 nanoseconds slow corner, 1.5 in typical and 1 in fast corner. If you look at the B to Y path, how much it takes if you take the fast corner, and how much in a typical corner, and how much we need to calculate. But as a part of the constraints input, targeted constraints, you have a constrained, delay constrained on that B to Y, let's assume that 7 nanosecond. Target is 7 nanosecond, means as per the specification, the delay between the B to Y is the 7 nanosecond. We should not cross the 7 nanosecond. That is a constraint given as a part of your constraint file. Now, take the fast corner. If you add the delays for the 4 gates, 1 nanosecond, 1 nanosecond, 1, 4 ones, 4 nanosecond, which is less than the 7 nanoseconds, means you met the given constraint. And go to the typical corner. What are the delays for each gate? 1.5 nanosecond, 1.5, 1.5, 4.5, 6 nanoseconds, which is less than 6 nanoseconds. Go to the slow corner. Slow corner, each gate has the 2 nanoseconds. 4 twos, 8 nanoseconds. 8 nanoseconds, which is more than 7 nanoseconds targeted value. Means, if you look at the slow corner delays, is not meeting given constraint value. But in the remaining cases, typical case and fast case, you are able to meet. That is not sufficient. We should meet this delay constraint in 3 conditions. In which conditions we are not able to meet after mapping? In slow corner, because you are seeing more delays in slow corner PVT condition. That is the reason we should choose the slow corner libraries for the logic synthesis, because if you meet these performance or delay targets in slow corner, definitely you can meet those in typical and fast corner, because you have the less cell delays in that one, in those conditions. Okay. Now, I'm taking the targeted PVT condition, nothing but slow corner PVT condition. I chosen that. Now, your delay is 8 nanoseconds, but target is 7 nanoseconds. How can meet? Because it is called violation by 1 nanosecond. I should meet this constraint. What I can do? That is called optimization. That step is called optimization. After mapping, we should go for the optimization. If you see any violations, means you are not able to meet the given target constraint. As a part of optimization, One is logic optimization and one is the cell changes. Means logic restructuring one, and one is we can change the cell type. Logic optimization means same logic, whatever the logic you are seeing in the diagram, A to Y, B to Y, all are similar logic, same logic, functionally should be same, can be realized using the less number of gates. That is called logic optimization or logic restructuring. These logic synthesis tools are able to do that. By looking at the constraints after mapping, if any violations are present, if you are not able to meet the design targets, then tool will go for the logic restructuring to meet those constraints. That is called logic restructuring. Realize the same functionality with a minimal number of gates. And one more is replacing the existing standard cells, existing gates. What is that? Every library contains inverter, AND gate, OR gate. It is not a single inverter. It is not a single AND gate, OR gate. Depends upon the width of the gates. They will provide the multiple cells for each and every functionality. Inverter is one functional cell, AND gate one function, OR gate one function, buffer one function, like that, and flip-flops. For each and every functionality, they will provide the multiple gates. Depends upon the width of the gates. Okay, let's say inverter X2. X2 has some certain width. Inverter X4 more width. Inverter X8 some more width. These are multiple cells under same functionality, and 2x2 and 2x4, like that. By changing the width of the these cells, you will see the change in the parameters like cell delay and power numbers. So not only logic restructuring, we can swap the cells also. Let's say in your design, if you take the previous example, you have the 1 nanosecond violation. You want to replace existing AND gate or OR gates with less delay AND gates, OR gates. Means if you go to in general, if you go to the more width, you will see the less cell delay. Okay, you can replace existing. Let's say you have the AND 2x2. You can replace that AND 2x2 with AND x4, which can drive more load. You may see the less delay, faster response at the output, less propagation delay. That is one kind of optimization. As a part of this optimization, whenever the tool sees the violation, it will go for the optimization, logic restructuring or cell swapping. So, by doing this optimization, first we should meet the performance target, your performance target. Then two more targets are there, power and area. While doing this performance optimization, we should not go for the unnecessary optimization. Means, if you go to the previous example, by replacing X2 cell with X4, next width cell, next drive strength, if you are able to meet your delay constraint. But if you go to the X8, really X8 is not required. It's a bigger cell. Of course, you can see the better delay, but really it is not required. If you go to the X8, because of the more width of the transistor, your area increases, your power increases, which is really not required. Means what? We should meet the performance with the least possible power and area. We should choose the optimal cell so that you will see the least power and least area with the best performance. That is called PPA target. In essence, the whole target is to convert RTL into the gate level net list by meeting PPA targets. I think we are getting a call. Let me answer that call before going to the next step. Hello?
Hello.
Yes, please.
Sir, I have completed my BTech.
Okay.
If I need to start a career in semiconductor design, will you going to guide me, sir?
Yeah, sure. In my coming slides, I will explain about the career opportunities in this physical design domain. What are the eligibility criteria and what are the ways to enter into this physical design domain. All I'll explain in coming slides. Okay? Back to our discussion. So, we should meet these PPA targets while converting this RTL into the gate level netlist. That is the whole process of synthesis. Translating into the gates and mapping to the particular technology, and optimization depends upon the violation. Okay. The output of this logic synthesis is optimized gate level netlist. So, we converted entire RTL into the gates. We started with the design and then coding RTL. Now, it is in terms of gates, logic gates, digital gates. So, output of synthesis is your gate level netlist. That is input to the next stages. After synthesis, entire design in terms of gates. In fact, the entire design is converted into a sequential circuit. If you recollect your academics, a sequential circuit as shown in the diagram starts with a resistor, going through a combinational logic and ends with a resistor. A resistor is nothing but a memory element, flip-flop, latches or any SRAMs, your RAMs. These are called memory elements, sequential cells. Typically, entire design is converted into a sequential circuit as shown in the diagram. If you look at the bottom diagram, first one is the data one, that is your I/O pad, input to your chip. That is going to a logic, that logic is going to the D pin of your flop. Generally, you have the different sequential cells, right? JK flip-flop, D flip-flop like that. In general, people use the D flip-flops for in ASIC design. So, that is the D pin of the flop. Started with your I/O pad and going to the D pin of the flop. And next one, path 2. Start with the sequential cell and end with the next sequential cell. I am showing only one path, one flop to flop, flip-flop to flip-flop path. But you have the multiple paths, depends upon your design. And finally, the output of this resistor is going to the output pad of your chip. If you look at the diagram, what tells us, the entire design is converted into the input to resistor, resistor to resistor and resistor to the output port, output pad. Whole design is converted into a sequential circuit. If you look at the performance means frequency. One more input pin you observe in the diagram, flip-flop has the CK pin, means clock pin. We need to apply the clock also. Clock with certain clock period. That clock period is nothing but frequency of your design. As you know, F is equal to 1/t. If you have least number, clock period number, then your chip is operating at more frequency. How can you achieve that least possible time period? I will explain. If you see, take timing path 2, means from flop to flop. The clock to key delay of the flop, the combination delay of the logic, and generally every flop has some internal delay, that is called setup time requirement. All these adding means your signal start from the first flop and coming out of this flop after clock to key delay and going to the logic. After T logic, you are seeing the signal output of that logic and it is going to the next flop D pin. Internally, we have some delay, it is called setup time. By adding all those values, it should be less than the clock period of your design. If you are able to meet this equation, you can say your design is running at particular frequency. Okay. How much you can optimize this delay? Least possible clock to key delay, least possible combination logic delay, least possible setup time. If you minimize those delay, your clock period will be reduces and you can see the high frequency. Of course, this frequency is decides early stage of our ASIC, nothing but as a part of specification. But by doing the proper optimization, you can achieve the best frequency. As a part of your synthesis, after completion of your synthesis, you need to look at already your frequency time period decided as a part of constraint file. you should take the time period from that constraint file. And you are seeing the delay values from the gate level netlist by reading the timing libraries. For flop, for a combination cells, you have the delay numbers from the timing libraries. As we discussed, we read the slow corner timing libraries. You have the functionality, each flop, flop and logic, and all these function cells delays you are getting from the slow corner, and the target clock period you are getting from the constraint file. By getting all those information, the tool will measure this equation. It check for this satisfying or not. If this equation is satisfied, we can say our design is met for a given frequency. You are able to meet the given performance by choosing the least possible power and area. That is the goal of synthesis by checking this equation. Similarly, path 1, input to D pin. Path 3, flop to output port. We should check this equation, this is called timing equation, timing check. This check we should do for all the paths available in our design. I am taking one path, it is called resistor to resistor, reg to reg. I am taking one path, but whole design is converted into the multiple paths. Okay, for all timing paths must satisfy this equation before going to the next steps with the least possible power and area. That is the goal of synthesis. I think we are getting a call. Let me answer that call.
Hello.
Yeah, yes, please.
Sir, my name is 𝗬𝗧𝗧 𝗚𝗧, sir. నేను బీటెక్ 4th year చదువుతున్నాను, CSC background, sir.
Okay.
Could you please guide me, sir, how to join an internship in Moschip, sir?
So, what is your qualification?
Sir, CSC, sir.
CSC, Computer Science Engineering, right?
Yes, sir. Yes, sir.
Yeah, generally Moschip, for Moschip eligibility is ECE, Electronics and Communication Engineering. CSC people are eligible for the software side, and one more group embedded systems like that. But for the VLSI, the eligibility criteria is ECE and AAA, Electronics and Electrical and Communication Engineering. Yeah. So once synthesis is completed, the output is optimized gate level netlist along with your targeted constraints. Yeah. Once RTL synthesis completes, we need to go for DFT and STA. Yeah. Let me talk about DFT before going to that one. DFT means design for testability. That is one more department in the ASIC methodology. Yeah. Design for testability. Okay. Yeah. I will give you more details in the coming slide. Yeah. First is RTL synthesis. Already we discussed converting RTL to the gate level netlist by meeting PPA, and output is the gate level netlist. Once we get the gate level netlist from the synthesis tool, we need to check for the STA. STA means static timing analysis. We need to do the static timing analysis, whatever we discussed so far, the timing equation, clock to Q delay, T logic plus setup time requirement should be less than the clock period. That check is called static timing analysis. If the STA is clean, no violations, then you can go to the next step. If the STA, you have some violations, as we discussed, we need to do the optimization by rerunning the synthesis or by changing the design. Okay? Yeah, once STA timing is clean, then next step is the DFT logic insertion. We should insert the DFT logic, design for testability logic. What is this DFT? Importance of this DFT stage. After manufacturing of your chip, you may see manufacturing defaults. The chip can fail in two ways. One is the design. If the design is not correct, you may not get the intended output. And one more is the fabrication failures. Sometimes fabrications may not be happened as expected. To know the manufacturing default after fabrication, we need to insert some logic, that is called DFT logic. We have separate group. So we should insert that logic on the gate level netlist. After inserting this DFT logic, we call it as a post-DFT gate level netlist. After inserting this DFT logic, we need to run for the LEC, logic equivalence check. It is functionality verification. After converting this RTL and after inserting this DFT, make sure we should not lose our functionality. To verify the functionality, what we need to do, we should run the logic equivalence check. Once the logic LEC passes, then that will go to the physical design. Your post-DFT netlist, LEC clean netlist, is input to the next stages. Nothing but your physical design. Physical design, place and route. We call it as a place and route. I'll let you know why we call it as a place and route. After synthesis, whatever the gate level netlist you are getting from this output of synthesis, that is input to your physical design. In your logic synthesis, we are talking about the parameters like cell delay and power for a gates. In fact, the gates are not placed. Physically, they are not placed. We have the connectivity. Based on the connectivity of the design, we are calculating the delays and we are calculating the power numbers. And for those numbers, we are checking the timing analysis, STA, as a part of your synthesis. But coming to the physical design, in physical design, the standard cell logic, whatever the logic present in your design, whatever the IPs, and what are the SRAMs you have in your design, all should be placed and routed. Connection between those gates, between the RAMs2 logic, all connections must be completed. That is called routing. You are placing all the components, IO pads, IPs, RAMs, standard cells, all placed in an area and we are routing them. All the interconnections are routed. That's why we call it as a place and route. Placing the logic and we are routing them using the metal layers. That is called place and route. In fact, what kind of checks we are doing as a part of logic synthesis, similar kind of checks like performance check, power check and area checks, everything we need to do even in physical design also. But the difference is we are placing and routing them. If you complete the interconnections, means routing, then one more parameter called net delay. It will comes into the picture as a part of physical design. We are doing timing analysis STA in logic synthesis. Also similar kind of timing analysis we need to do in the place and route also. But the main impact is we are introducing net delay. In synthesis, there is no routing happened. If there is no routing happened, you can't see the net delays because your resistance and capacitance values of the net depends upon the length of the wire. How can you get a length? By placing the standard cells. First, you should place the standard cells. We should route them. Then only you can see the net length of the wire. That is the main difference, key difference between the logic synthesis and place and route. Net delays. I think we are getting a call. Let me answer.
Hello.
Yeah, hello.
Sir, can you suggest me some important topics for the technical round of RTL design?
Yeah, for RTL design,
Yes.
we need to understand the design actually. RTL design team, better to have design knowledge and also Verilog VHDL, right? If you recollect our initial slides, right, I discussed about Verilog and VHDL. Please practice on Verilog and VHDL. It helps you good career in RTL design if you have good knowledge on that one. And also one more part, verification. Verification also will help you in choose a good career in the RTL design. Okay? So, net delay. Once if you place the standard cells, if you complete the routing of our interconnections, then you are able to see the net delays. Depends upon the net length of every interconnect. It is not a single net. You have the multiple nets, right? Depends upon the design. So, by including those net delays and also, one thing, net delays and cell delay. At the time of at the time of synthesis, whatever the cell delay we are seeing depends upon the load it is driving. Generally, that load capacitance depends upon the net capacitance also. But in the logic synthesis, you don't have net capacitance. Whatever the cell delay we are seeing without net capacitance. Now, by introducing the net capacitance after routing, your cell delay increases, because net capacitance increases, load capacitance increases. Now, whatever the cell delays we are seeing in the place and route, including this new net capacitance and also cell net delays, because you are getting the resistance and capacitance of the wire. Now, same timing analysis, clock to Q delay, the clock to Q delay with net capacitance. Then the output of the Q pin of the flop is connected to the logic, that net delay. And within the logic, you have the nets, those cell delays and net delays, plus that the net connected to the D pin of the flop, that net delay. By including all those new cell delays and new cell delays along with your net delays, we should do the similar kind of timing analysis, nothing but performance check within the given clock period or not. That check we need to do as a part of your place and route. That is the key difference between the logic synthesis and place and route. Of course, one more thing, foundry design rules. While doing this routing, we are doing the routing using the metal layers. We should follow the design rules coming from the foundry, like minimum spacing, minimum width and enclosure rules. We should follow all the design rules coming from the fab house while doing this routing. Basic inputs for any PNR, place and route. One is post DFT gate level netlist coming from the logic synthesis team, and next one is the timing libraries, whatever the timing libraries, let's say slow corner timing library, which is used as a part of logic synthesis, that is also input. And constraint file, whatever the constraints are using as a part of your logic synthesis, that constraint file is also one input. These three are coming from the synthesis team. Apart from these three inputs, two more inputs we required. One is LEF files. If you recollect our early discussions, technology files, I discussed about technology files, TechLEF, which is captured about all the metal layer information with all design rules given by the fab people, minimum width, minimum spacing and thickness, all those parameters. We should read that information also, because it is a place and route. It is a place and route. Because we are doing the routing, right? We should all the layer information for the delay for routing, for completion of routing. And macro LEFs. If you recollect, IO pads, IPs, standard cells, RAMs, all those are called hard macros. These are predefined cells, right, with a certain width and height, and also pin information. To load our design in PNR tool, we should require these physical libraries for all components present in your design, along with your TechLEF. That is one major important input for the place and route. And final one is area information. As we discussed, every chip is targeted for a certain area. As part of specification, they will come up with a area requirement. What is my die area? How much area is going to taken by my chip? The die information with certain height and width. That is one information. And also IO pad placement, input and output pad placement. My die will go and sit in the packaging. Depends upon the packaging requirements. These IO pads will be placed in all the direction of your chip. That IO information and die area you will get in a file called, through a file called def file. That is one more input, design exchange format, that is one more input file for the place and route along with other files. This is physical design flow. First step is design import. As a part of this design import, we should gather all the required files to start with our place and route. Already we discussed, right? 5 categories: gate level netlist, constraint file, timing libraries, def file, and left views. All these files we should read as a part of this design import without any issues. That is design import step. Once the design import step is completed, next step is the floor planning. Placing of bigger components. I will explain more details in the coming slide. Next one is the power planning, power and ground connections. Next one is the place optimization. To meet our timing targets, power and area targets, we should go for the place optimization. After that one, there are 2 parameters, congestion and timing. We need to look at those parameters. If those parameters are met, then you can go for the next step. Or if you are not able to meet this congestion and timing parameters, then you should go back to your floor planning. Next step is the clock tree synthesis. As we discussed, we have the clock for every ASIC. We should build the clock tree to supply the clock for each and every clock pin of your sequential cells. That is clock tree synthesis. Next one is, after clock tree synthesis, we should do the post-CTS optimization if you have any violations. If the design is not meeting your timing, we should go for one more round of optimization. That is called post-CTS optimization. Next one is the detailed routing of your signal nets and clock nets. Next one is the post-route optimization. After routing, if you have any violations, timing violations, you can do the post-route optimization. That is one more round of optimization. If you see, there are 3 stages, right? Place optimization and post-CTS optimization and post-route optimization. And after post-route optimization, then we need to dump out all the required files for the sign-off checks, which is our next stage. First, floor plan. As a part of design import, we are able to load all the required files. After loading of all the required files, we should start floor planning. Floor planning nothing but placing of the bigger cells. Bigger cells means your IPs and your SRAMs and your IO pads. All these we should place manually as a part of floor planning. As a part of floor planning, we should place all them by following a floor planning guidelines. We have some floor planning guidelines for better optimization. We should follow all those floor planning guidelines and we should place these SRAMs, IPs and IO pads. Of course, IO pads already we will get initially, and we should place these macros and IPs. Okay, that is floor plan step. Next one is the power plan. In power plan, we should design the power grid, power and ground, VDD/VSS. Entire chip, we should have the power and ground. All the standard cells, macros, IPs, all components in your ASIC must get the power and ground. That power and ground routing will be happen as a part of this power plan. After power plan, make sure we should not see any opens or shorts in the power and ground nets. That is a major check. Okay. So, every cell must get the power. If any cell is not getting the power, that is an issue. That is called open. Similarly, we should not get any shorts. Such a kind of checks we need to do after completion of your power planning. And the main goal of the power plan is, one is supplying required power to the cells, and also the drop. If you recollect, as a part of timing libraries, we discussed about the voltage drop. right? Because of the resistance of these power nets, we are seeing some drop. The drop should be within a given range. Generally, the range is a 10%. That range is a 10% range in general. So, the drop should be within the given range. To meet the target drop, we should design our power grid. Next one is the placement and optimization. We should place all the standard cells as a part of this placement. In fact, it is a automation in the PNR tools. By giving some commands, tool is able to place. The PNR tool can be able to place all these standard cells by following our floor planning. The floor plan is the key for this placement of the standard cells. If you want to get the better placement, then your floor plan must be good. By following all the floor planning guidelines, if you come up with a good floor plan, then you can see the better placement and optimization. After placement of the standard cells, then if you see any violations like timing violations, transition violations and congestion. One more topic, congestion. I will explain what do you mean by congestion. First, tool will check for the timing violations. If tool sees any timing violations, then tool will go for the optimization. As a part of optimization, we can change the floor plan again, or also what we can do by changing some of the tool options. Again, we can rerun the placement to see the better timing and also congestion. Congestion means the routing, right? So, whatever the routing we are talking, right? So, we have the routing tracks to complete the routing in the coming stages. Still, we are not at route stage. But to get the quality routing, what we are doing, we will check the congestion. Congestion means measurement of the routing tracks, quality of available routing tracks in the core area. To complete the routing in the coming stages without any violations, we should have the sufficient routing tracks. Those sufficient routing tracks are available or not in your design, we can see by looking at the congestion number. Okay? If congestion, you have any congestion, again we need to fix that congestion before going to the next steps. Congestion means routing tracks are not sufficient to do the complete routing in the coming stages. So, that is one more important check as a part of our PNR, congestion check. Once the congestion and timing is met, then you can go to the next stages. Next stages. This is one more representation of your placement of the standard cells. If you look at those, you have the colors, right? Red color, green, yellow and blue. For good identification, generally we prefer to give the colors. If you look at the red color, the bigger cells, nothing but your SRAMs, are highlighted in the red color at the top right. And the remaining red, it is a logic. That is one module. As we discussed, entire design is made up of some modules. Green color is one module, red color is one module. Module contains the standard cells and macros, SRAMs. We are placing all module related macros in one side. We should not mix the different module macros. Then that is a problem. We should place the module related macros in one area so that you can expect the placement of the standard cells closely to that macro group. If you place the standard cells in a closed fashion, your net length will be reduces. The whole idea of the placement and optimization is to reduce the net length. If you reduce the net length, you can see the net delays are less number of routing tracks are required, means your congestion becomes less, and also you can see the better cell delays. So, the whole idea is to minimize the net length. For that one, what we need to do as a part of floor planning, the module related macros must be placed together, and also we are expecting the logic related to for the particular module should be placed nearer to that macro group. If you see green color, yellow, all are placed in that fashion. Then I can say my placement is good, done properly. Then I can see the less congestion and better timing. I think we are getting a call. Let me answer before going to the next slide. Hello?
Hello.
Yeah.
Sir, in present first year BTech ECG చదువుతున్నాను సార్ నేను.
Okay.
VLSI లో ఎన్ని డివిజన్స్ ఉన్నాయో ఒకసారి తెలుసుకోవాలనుకుంటున్నాను సార్ నేను.
Yeah, definitely. In fact, I am covering one of the slide. In coming slides, one of the slide about different domains in VLSI. Surely I'll cover in the coming slides, okay? Thank you. Yeah, after placement, clock tree synthesis. Next step is the clock tree synthesis. Every flop, every sequential element has the clock pin. We should supply and we should give the clock to the each and every sync pin. So, as a part of clock tree synthesis. Logically it is connected so far, but we should place them. We should give the clock to the sync pins without any transition violations on the clock nets. Okay. First is insertion delay. What is insertion delay? The delay from the clock source to CK pin of the any sequential cell. It is called clock insertion delay or clock latency. Every sequential cell has the insertion delay, nothing but latency. The main target, we should build the clock tree in a such a way, we should see the best possible insertion delay, means least possible insertion delay. That is one of the important target of the clock tree synthesis. Without any transition violations, we should meet this insertion delay target. That is one thing. And next one is the clock skew. The difference in the insertion delays of the sequential pins. As I told you, each sequential cell has its own insertion delay. The difference in the insertion delay is called clock skew. If you take in this diagram, there are 3 flops. 3 flops has the 3 different insertion delays. Depends upon their placement and the way clock tree is built. The difference in the insertion delay is called clock skew. As a part of clock tree synthesis, we should achieve the least possible clock skew and least possible insertion delay. That is the main targets of the clock tree synthesis. Because your clock skew also will impact your timing check. Actually, so far we are seeing one timing check. That as a part of STA, right? We are checking clock to queue delay, combination delay, and setup time requirement less than the time period of the clock. That is called setup check. And one more check is called hold check. Means what this STA is talking, right? Setup check and hold check. Hold check means the data which is coming from one register to the one register and going to the another register. It is the start point is called launch register. End point is called capture register. The delay between this launch register to the capture has some constraints, minimum delay and maximum delay. Means we should not have the delay between the registers less than the minimum delay target. And we should not cross the delay maximum delay constraint. Means there is a range of delay, minimum delay and maximum delay. The maximum delay constraints already we verified as a part of setup check in synthesis and even in PNR also so far. And one more check is minimum delay constraint. Means every timing path should have the delay more than that value. That is called hold check. There are 2 timing checks, setup and hold check. Okay. After completion of your clock tree synthesis, the clock skew comes into the picture. Now onwards, as a part of STA, timing analysis, we should do the setup check as well as the hold check also. After this clock tree synthesis, detailed routing. Okay. Now we should finish the routing of the interconnects. All the connectivity, all the interconnections like one gate to another gate, right? You have the interconnection. That is, those connections should be completed using the metal layers as a part of detailed routing. Routing will be happened, this one. the main goal of the detailed routing is we should not see any DRCs, means design rule check. We should not have any design rule violations. If you recollect our early discussions, tech file, which contains this metal layer information with rules, minimum spacing, minimum width, enclosure rules, all those rules we should meet after completion of this routing. We should not have not even single violation after this detailed routing. That is called a DRC check, design rule check. Now, once the detailed routing is completed, if you see any DRCs, if you see any timing violation, you can go for the post-route optimization, right? I think if you look at our physical design flow, you have that step, post-route optimization. If you have any violations, if you don't have any violations, you can go to the next step. Next step is the outputs for the sign-off. Once your place and route is completed, placement of the standard cells, clock tree building and routing completed. Now, we should dump all the required files for the sign-off checks. Okay, I will explain what are all the sign-off checks. Before going to the sign-off checks, what are all the files we need to dump on the post-route optimization design? Post-PNR, generally it is a post-PNR because place and route completed. Post-PNR gate level netlist, post-PNR gate level netlist with power and ground pins, and post-PNR def. Generally, the def contains physical information of your design, routing layer information, placement of the standard cells, all this information you can capture in the def file. And GDS2, this is one more output file from the PNR tool, graphic design system, it is GDS. These are all different files for the different sign-off checks. STA, LEC, LVS, IR drop and PV, physical verification. I will explain in the coming slides. Sign-off checks summary. First is RC extraction. Whatever the timing you are seeing as a part of place and route so far, post-route optimization, post-route optimization means timing optimization. There also we have the resistance and capacitance of the nets. But now that is not sufficient. We have to go for separate check, separate extraction called sign-off RC extraction. Right? For that, we need to do the sign-off RC extraction from where you will get the resistance and capacitance for each and every wire. That is one thing. Next is static timing analysis, STA. In logic senses, we did STA. In the place and route, we did STA. But still, that is not sufficient. We should run one more round of static timing analysis using the sign-off tools. That is a STA, sign-off STA. Next, IR drop analysis. As we discussed, as a part of power grid analysis, power grid plan, we should define the power grid in such a way the voltage drop within a given limit. We did the power grid plan. But we need to verify that whether the voltage drop within the acceptable range or not. That is IR drop analysis. Next one is logic equivalence check, LEC. This is confirming your functionality. On the final database, sign-off LEC check we need to do. And next one is the physical verification, DRC and LVS. Of course, we are doing the design rule check as in PNR also. That is opens check is called connectivity check, LVS. That is also we are checking in PNR, but that is not sufficient. In sign-off physical verification, we need to check DRC, LVS. These are all called sign-off checks. Okay. Once the sign-off checks are completed, then the final GDS is input to your fabrication. That is called a taping out. We are giving GDS to the fab for the fabrication. That process is called tape out. Okay. One is GDS format and another one is the OSS format. I think you looked at those formats in the previous session, layout session. OSS and GDS are the two different formats in which we can send entire chip database to the fab. Static timing analysis is a part of this sign of static timing analysis. We should do the setup check and hold check for all PVT corner libraries. You have the 3 PVT corners so far we discussed: slow corner, typical corner, fast corner. For all PVT corners and given constraint file we discussed as a part of logic synthesis and PNR. For those constraints, we should check, setup and hold as a part of this static timing analysis. And also, if you see any violations, if you see any setup violation and hold violations in the sign of timing analysis, then we can implement those violations as a ECO, engineering change order. Generally, if you see huge violations, then again we need to go for the PNR as a part of optimization, those violations. But the violations are handful, less. You can implement those violations on the post-route optimization database in ECO's manner. And apart from this STA, one more called SDF check. We need to provide the SDF, standard delay format. This is to verification team. We should provide each and every delay of the gates in a SDF format for the delay annotated gate level simulations. This is called GLS to the verification team to ensure one more round of check apart from this STA check. Then IR drop analysis. We are giving supply at power pads. That power pad supply is going to the standard cells or IPs, any component in your design in core area through metal layers. That metal layer has some finite resistance. Because of this resistance and the current flowing through these metals, because the standard cells or IPs or the SRAMs, all these cells will draw current. The current flow through these metals. Current I and resistance of the metal R. This is called IR drop, voltage drop. You are applying, let's take for understanding, you are applying 1 volt. Let's say you have drop 0.2 volts, 1 minus 0.2, 0.8, what is the gates are getting. That is the meaning of IR drop analysis. If my target is 10%, means 1 minus 0.1 means 0.9. Each and every standard cell or IPs, any component in your ASIC must get at least 0.9 volts or more than that. 0.9, 0.95 or 0.96, any value more than this 0.9 volts. That check we can do as a part of IR drop analysis. Each and every instance must get the voltage more than this 0.9. That check as a part of IR drop analysis. Yeah, before going to the next step, I think we are getting a call. Let me answer that call. Hello?
Hello. Sir?
Yes.
Hi, sir.
Please.
Sir, my name is Lata, sir. Warangal నుంచి కాల్ చేస్తున్నాను. నా క్వశ్చన్ వచ్చేసి, what are the common techniques used to reduce the dynamic power in clock tree, sir?
Okay, dynamic power in the clock tree.
Yes, sir.
Okay. See, generally in the clock nets, clock is called high frequency net. So, you can see the more dynamic power in the clock nets. First is, we should build the clock tree with less insertion delay. Means, minimum possible buffers in the clock path. Generally, clock tree built with clock buffers, which are in general bigger size. If you minimize the number of cells in the clock path, clock buffers or inverter pairs, if you reduce them, you can minimize the dynamic IR. Because first of all, the bigger cells count is reduces. By reducing that, power will be reduces because less number of gates. And also, the switching will be reduces. Already is a high frequency net. So, by meeting the latency targets, means by achieving the better latencies, insertion delays in the during the clock tree synthesis, we can minimize the dynamic power in the clock path. Okay? Yeah. Let me go back to our discussion. IR drop analysis. So that check, the minimum voltage requirement we can do, the check we can do as a part of IR drop analysis. Okay? Every gate must get the required voltage. Otherwise, it leads to the timing violations and also malfunction, means functional failures also because of noise margins. Next sign-off check is the logic equivalence check. This logic equivalence check is 3 stages. One is RTL versus post synthesis, means after synthesis. Already we discussed. We did the logic equivalence check after synthesis, that is RTL versus to post synthesis. Next one is after completion of your place and route, post PNR netlist, gate level netlist you will get. Post PNR versus your post synthesis, that is one LEC check. And third one is post PNR gate level netlist versus the initial RTL, initial your design. So in all stages, LEC must be clean. Then you can say your functionality wise, we are good. That is sign of LEC check. Next one is the physical verification, DRC and LVS. As we discussed, every fabrication house will provide you set of design rules. We should complete either analog design or digital IC. Everyone must follow these design rules. Okay. But if you don't follow the design rules, you may see the DRC violations in the physical verification. If you have any DRC violations, fab people won't accept our GDS2 or OSS. So you must clean the DRCs as a part of this sign of physical verification check. And also LVS, layout versus schematic. What is the layout? Your GDS2 is our layout, which contains all the design information from the device level. In device level, GDS2 is a device level format. You have only layers. So for complete chip, in device level, we need to verify this DRC as well as the LVS also. Our GDS2 is the layout. And we are dumping one more netlist with the PZ pin as a part of our outputs. That gate level netlist, post PNR gate level netlist with PZ is called schematic. Whatever the connections present in this post PNR netlist, PZ connections and signal connections and all connections must have the logical connections must have the physical connections in the GDS2. That is called layout. LVS. That is called LVS. Layout versus schematic. Whatever the logic connections present in the schematic must have the physical connections. That check is called LVS. We should not have any opens. We should not have any shorts. So, as a part of sign of physical verification, we must complete DRC LVS before sending our GDS to the fab. Once DRC LVS is clean, tape out our GDS to the fabrication. Once fabrication is complete, you will get the dies of your chip. Those dies we should send it to the packaging team. To prevent from the external environment, we should go for the packaging. There are different packaging styles. Okay. So once packaging is completed, you will get the packaged IC, which is going to the labs to verify our functionality of the chip. That is the whole process of our ASIC design. Starts from the specification, ending with the packaged parts. Of course, we need to do the testings in the labs also. Okay. That is about ASIC design methodology. Now comes to different tools, EDA tools we are going to use as in our ASIC design methodology. First one is logic synthesis, RTL to gate level netlist, Cadence GNS and Synopsys DC design compiler. These are the two famous tools for the logic synthesis available in the industry. Next one is the place and route, gate level netlist to GDS, Cadence Innovus and Synopsys ICC2. Okay, and logic equivalence check for LEC, Cadence Conformal or Synopsys Formality. These are the tools for the LEC. And physical verification, DRC LVS, Cadence PVS, Physical Verification System or Pegasus. And in the Synopsys, we have IC Validator and Mentor, I think now it is Siemens, Caliber tool for the DRC LVS, physical verification. For airdrop analysis, Cadence Voltus and one more famous tool is Apache tool vendor. Red Hawk is the tool name, Apache Red Hawk tool. For RC extraction, Cadence QRC and Synopsys Star RC. These are the tools for the extracting resistance and capacitance from your design on the post PNR database. And for the STA, static timing analysis, Cadence Tempus and Synopsys Prime Time. These are the tools. For GDS or layout viewer, generally these PNR tools are not capable to load this GDS. We can't see the base layers, poly, well layers in the PNR tools. If you want to look at complete design information in a layer level, that is called GDS or layout viewer. We can use the Cadence Virtuoso. Now, different VLSI companies, product companies, first one, and next one IP based, and next one is the service based. Product based companies are, it is a responsibility to deliver the complete product as laptop, smartphone, smart TV, all comes under products. Complete product is delivered by those companies. Intel, Nvidia, AMD, Samsung, Apple, these are all famous product companies in the industry. We can have the opportunities in those companies also. All kind of opportunities. Next one is the IP based companies, IP based business. If you recollect our initial slides, right? IP, I used word IP. PLL. One of the IP is PLL for the clock generation. Right? So that is one IP. Similarly, you have the different IPs. DDR is one IP. USB. Like that. You have the different IPs. Depends upon your design requirement, we choose the IPs. Those IPs are ready-made, available in the market. Depends upon your design requirement, right? We choose the IP. The IP is available in the market. Synopsys, Cadence, those companies provide these IPs as a hard macro, direct IP. You can get it. That is one thing. You have the opportunities, jobs in those companies also. Next one is the service based. In the service based, you have the manpower, engineers similar to other company, product and IP based, and these engineers can work on the internal work, means you can get the work from any product based, IP based companies. You can work on those work. I can give an example. These product companies or IP based companies can take engineers from the service based during their execution time. Okay, you can find the jobs in service based also. Opportunities in physical design. First one is eligibility. We should complete bachelor's or master's degree in electronics communication or electrical and electronics engineering. I think nowadays VLSI, MTech VLSI or MTech microelectronics. These are all eligibility criteria to enter into this physical design domain. There are different ways to enter into this physical design. One is campus placement. nowadays the demand increases. Okay, some of the companies are going to the campus hire. Even our Moschip is also going to the campus hire. That is one way of entering into the physical design. And next one is the internship. Companies will offer the internship also in the final year or after completion of your graduation. They will offer the internship. One is internship. So they will, as a part of internship, they will provide you some work. Okay, after completion of internship, they can hire you as the employee. That is one way. And third way is training from a institute. You can complete your standard training for any good institution. After completion of your training in physical design, you can get opportunities in multiple companies. Yeah, one of the good institute in Hyderabad is Moschip Institute of Silicon Systems, MISS. It is very good institute for the physical design training. History started in 2012 and we trained so far 1,000+ engineers, and they are placed in a good companies. They are in good position nowadays. If you go and look at any good company, mostly you can find these MISS students. They are very well placed in good companies. And we are providing training on the industry standard tools. Generally, we prefer cadence tools for the place and route training, physical design training. Duration is 22 weeks. It's a full-time training. In typically, it starts somewhere 9:30 morning at 10 and until 7 p.m. or 6:30 p.m. It's a full-time training. Okay. If you want to go for more details about this training, you can call number on the screen, or you can mail, or you can browse this site. You can see more details, eligibility criteria, syllabus details, how to enter into this institute, all those kind of details you can get by looking at those, by contacting them. Next one is the different domains in ASIC design. I think one of the today's question or caller question, right? One is design or architecture. You can have opportunities in design and architecture level. Next one is RTL coding and verification. This is the one more domain where you can start your career. And next one is implementation. Implementation group. It covers synthesis, nothing but logic synthesis, whatever we discussed today, and LEC, logic equivalence check, and static timing analysis. These all comes under implementation group. You can find opportunities in this group also. And next one is the DFT, design for testability. This is one more domain where you can find opportunities. And next one is the physical design, place and route. Physical domain concept, place and route, physical verification, EMI analysis, and STA. In physical design also, you can find job opportunities. That is one domain. These are the different domains in VLSI. Apart from this, if you recollect the last week's session, analog design and analog layout, those two more groups where you can find opportunities. So these are all different groups in VLSI. Thank you guys. I completed my session, and thanks a lot. Thanks everyone.